Thank you, the organizer, for the invitation to be here. I also thank for the opportunity for myself and my students to be here, interact, and learn many interesting things in topos. I will talk about the work of other students that are not here. It's the abstract. So I split the presentation in two parts. It's not quite a preliminary part, but just references for that we will compare with the results we get, and then the proper talk. Okay. So pre-sheaf is just contravariant factor. Morphisms of pre-sheaves are natural transformations. We have the category of pre-sheaves. A sheaf over a topological space. We all know what is it. This can be represented, encoded by this equalizer diagram for each covering. We know that this depends only on the poset of the associated to the topological open set of a topological space. As we saw, a local is just a complete lattice satisfying this distributivity law. It's the same thing with complete Heyting algebra. And we can reformulate the notion of sheaf over a quantale as the same diagram, replacing intersection by meet. And a locality topos is just a subcategory of the pre-sheaf category of the all given by the all sheaves concerning this property. So, in particular, the subobjects of a home functor, that's a sheaf, is represented by these initial intervals, and a locality topos is a Grothendieck topos where the subobjects of the terminal object are generated for the topos, and a Grothendieck pre-topology on a small category with pullbacks or finite limits is a family of where each member of the family is a family of arrows with a specified codomain, satisfying these properties. A singleton given by an isomorphism is a covering. The transitivity axiom that coverings composed by covering is a covering, and stability under pullbacks. For locals, this is the same thing. An example of these topologies given by the subcovering in a locale, and the stability axiom. We put just a member below some u, maybe v less than u, and the distributivity of the locale, the distributive law, gives us the stability property is equivalent to this. So we can define a sheaf over a category with finite limits or pullbacks and a covering notion, a pre-topology, just replacing the IFMA by pullbacks here and writing an equalizer diagram. And without loss of generality, Grothendieck topos can be written in this way, assuming that the category, the small category has finite limits, and we put there pre-topology. Of course, this is each pre-topology determines a topology, consider the sheaves that contains some covering. And this gives the same notion, the same category. And many natural examples of Grothendieck toposes that can be characterized in many different forms. For instance, category is a Grothendieck topos if there is an adjunction like this related to the category E, that is a Grothendieck topos, with a pre-sheaf category where the right adjoint part is fully faithful and the left adjoint part preserves finite limits. Or also other characterization, a Grothendieck topos is an elementary Liouville topos, Liouville-Thielen topos, elementary topos, that has a small set of generator and is complete. Or alternatively, in 4 and 5 we saw the logical part of the elementary topos, and 1, 2, 3 we saw the Grothendieck expression of the topos. So the category should be complete, co-complete, locally small, of course, and kappa accessible for some regular cardinal kappa. The combination of 2 and 3 means that the category is locally presentable, kappa locally presentable. So an elementary topos is locally small, has finite limits, and in the presence of other axioms, this implies that it has also finite colimits. Admitted the exponential law for the product, like this, and has a subobject classifier that is a form that we can represent the contravariant functor of subobjects in this way, by this pullback, as we all know. And every Grothendieck topos is an elementary topos, but the category of finite sets is an elementary topos that is not a Grothendieck topos, since it's not complete or complete. So a bit of internal logic of topos. For a local topos like sheaves of local L, we have the very concrete presentation of the subobject classifier as a pre-sheaf, where the value of this pre-sheaf on an element of on a member of the local is just this initial interval, the things above a new. And restriction is restriction given by info. And this property of the classifier, in fact, gives the subobjects of the home functor, that is a sheaf, is just an initial interval. And the subobject classifier encodes the propositional logic, in some sense, encodes the propositional logic internal to the topos. So, it's an internal Heyting algebra, therefore there is this adjunction law for the infima and implication. And internal operations corresponds by classification and in Ioneda lemma to external operations in the poset of the subobjects that in fact is a set. Every topos is well covered. So another presentation of locality topos. Many of you, of us, saw the lectures of the Professor Isa Stoop. So we more or less okay with this version. And L set is just a pair given by a set X with a codistance operation or a codistance relation. It's better this way. It's a kind of partial equivalence relation satisfying the axiom of symmetry and transitivity like this. And we note that it holds also this law for idempotence. It's very easy to derive this. And there are two ways to compare L sets by functional morphisms that are some functions satisfying some property of preservation of extent and increasing, being a co-contraction, let's say. And another natural notion is the relational morphism that we saw also in the presentation of Stuck. There are many special subclasses of L sets. In particular, I point out the subclass of Scott-complete L sets that is a combination in the language of enriched categories of the property of being skeletal and that in L set maybe can be said like separability property and also Cauchy completeness. So it's the same thing in other language. Every L set has a Scott completion. This provides a left adjoint to the inclusion, like this. And it's well known that the locality topos has many equivalent representations, like sheaves over local L. And the subcategory of L sets that are Scott complete and functional morphisms, or the category of L sets that are Scott complete and relational morphisms, or, and this is isomorphism, the category of L sets with all L sets with all relational morphisms, and also a category that can be built from the expansion of the universe of the sets by the local and taking some quotients. The objects are classes of equivalence of these elements of the universe extended by the local, and the arrows are classes of equivalence of some things that the universe see as a function. This you can find this sketched at the end of the book of Bell's book of models for independence, Boolean value models for and proofs of independence. Then we arrived to the subject of the talk. Our motivation was to consider some form of monoidal topos theory. Was practical motivation in one side, meaning we arrived to very simple and natural notions of sheaves that are not are expressed by usual versions of the notion of sheaf. Like we can, for instance, consider a metric space giving many forms of sheaves, but concerning more the lovely quantale. We try to, in some future, relate this with continuous logic. Another part is connection with rings and affine schemes. Sorry, oops. Yeah. And try to produce other expressions, mathematical expressions like check homology of a topological space can be identified with the check homology of the quantale associated to the quantale of ideals of the ring of continuous functions, like Peter and my student have done. And also another motivation was a theoretical one. There are interesting categories with a non-intuitionistic internal logic. So in Brazil, our reference to quantale versions of sheaves are the work of Miralha Conilho, but on sheaves over right-sided idempotent quantale. And we are aware of the work of Ulrich Hohl, and we learned a lot of things with Isaac Stubb last week. But at the times, we are not aware of this. So a quantale for us is just a complete lattice, and that is a semigroup, and have these both the distributive laws. Of course, every quantale every local is a quantale in this way. If you fix a commutative ring with unit, the set of ideals satisfied with the product of ideals satisfies these laws. Of course, we can consider the non-commutative case and just take the right ideals or the left ideals and multiplication. The Liouville quantale is a very nice example. We hear about also the quantale 0, 1 with other key norms, and the closed right ideals of C-star algebra with the proper multiplications, interesting as example also. Some subclasses of quantales. The unital quantales are the quantales where the semigroup is in fact a monoid. A quantale is idempotent when the multiplication is idempotent, and is semicartesian when the product is less than A times B is less than A and less than B. That's the same thing to require this inequality. And it's easy to see that every unital and semi-Cartesian quantale require this. Is this same requirement to be a quantale that is integral or bounded? The unital and bounded. And this is to show. And the requiring the property of idempotence and semi-Cartesian, let's say, trivialize the theory because we get exactly the local. So we're trying to find other expression of sheaves and internal logics that are not have a multiplication that are not idempotent, in fact, since we don't a new phenomenon. Therefore, we are most interested in the first three examples that are unital and semi-Cartesian, are also commutative, but it's just for the first steps. But there are many other kinds of locales, evolutive locales and other stuff. Quantales, sorry. So for the moment, we assume that we get a quantale that is commutative and semi-Cartesian. Semi-Cartesian is the relevant hypothesis here. And this question is a very naive question. We have two forms of consider what is local topos, two essentially different forms of consider what is a local topos. So a quantale topos should be approached by two ways, in some sense compare the two ways, or compare the more importantly, compare the properties that of the categories that we build in these two different ways. So the first one is very naive one. We just replace the notion of covering is the same. soup. And the equalizer diagrams the same, where we replace infima by this quantale product. And of course, to this diagram make sense, we have to assume that we have these projections. This is exactly the hypothesis of the quantale being semi-Cartesian. And for instance, the affine scheme can be lifted to an example of achieving this scenario in this setting. Other examples are given by balls in a metric space, or pseudo-metric space. And another notion is the Q-set notion that's related, or strongly related with the rigid approach, and where we put a partial equivalence correlation Q-valued, where we assume the symmetry axiom, the transitivity axiom, and we put this another axiom that holds in every local to give some local units that in fact are idempotents. Other approaches given by Cristiani, where they put these two laws in one, a more general, in fact, law that implies this, both of them. And now I'll talk about the work, or parts of the work of Caio Mendes and José Alvim. Part of this ongoing work, other are well established. So the category of Q-sets and functional morphisms is completely analogous to the category of local value sets and functional morphisms in the terms of definition. And it's locally small, it's complete, it's easy to calculate the limits. It's co-complete, the co-products are easy, but co-equalizer no. But in fact, it is a kappa-accessible category, where kappa is this regular cardinal, okay? And from this we can obtain the co-completeness by Adamack-Koszewski theorems on locally representable categories and adjoint functors. It's a monoidal semi-Cartesian category with this tensor product, but we in fact have many of possible monoidal structures. This is the only one that's semi-Cartesian. That emits exponentiation, but not for this extreme condition, but the other extreme condition that not requires this vibration. In fact, consider exactly the all pairs of elements of the product, not with this restriction.
So what does the E mean in this equation? EX equals E?
Where? Extended this thing, yeah. Delta XX has idempotent because of this law. And okay, it has a classifier for regular superobjects, more or less trivial. Okay. But in fact, this is not the interesting category. Even for the local settings, the not interesting category. We are interested in a subcategory of this, of the Scott-complete Q sets that are the corresponding in the language of rich categories, the skeletal and Cauchy-complete Q sets that, but it's formulated in terms of singletons. So the existence part corresponds to Cauchy completeness, and uniqueness part corresponds to skeletal. Okay. So it's a reflexive subcategory. And if the quantale satisfies another property that is called a strong property, we found this in a paper of Ulrich Hall. Every quantale, every local satisfies this, and also the Lovir quantale obviously satisfies this. Then we arrived to the equivalence of these categories of complete Q sets that are commutative, semi-cartesian, strong for Q satisfying these properties. So complete Q sets and functional morphisms, complete Q sets and relational morphisms, and Q sets, all Q sets and relational morphisms. So this is one approach, a naive, from the part of quantum valued sets. Ana Luisa Tenorio have worked and still working in sheaves over quantales and generalizations in the functorial sense. Okay? So you saw the very straightforward way to generalize this for semi-Cartesian quantales. This category is locally small, is complete. It's very easy to see this. It's not at all easy to see that it's a co-complete category. In fact, this depends of this reflection property that if I do not have enough time. Okay. Okay, I will use the Blackboard to explain a bit. So it's a reflexive category. In fact, the same argument shows that it's cap-accessible for the same cardinal, regular cardinal that's in the quantale Q-set sense. So let me explain how this occurs, why this category is reflexive. This is a solution of the orthogonality problem in a locally presentable category. So we can represent, let's say that, sorry, we have here, we have we have a family F that is a covering. Oops. No. Okay. That's a covering of U. And we have a presheaf F. I already put in the assuming that we have a category because this is the same argument. That we will need in a few seconds, in a few minutes. So we can consider this, where this tensor product is the convolution in the presheaf category. We have the co-projections arrows. And we can consider the co-equalizer of this diagram. I will represent this way. And we have this diagram commutes, so we have a canonical arrow here, and applying natural transformations, meaning that if we consider the home in this category, this way, and apply this in this diagram, we arrive and call that colimits are transformed in limits. So we arrive to, oops. This diagram. I put this way, it's better. We are assuming that I will explain what the meaning of this in a few minutes. For the local quantale case, it's just the product, but in general case, we have to produce another concept. Sorry. Yeah. Oops. C op SF F, and here by Yoneda lemma. So this is an equalizer diagram here, and therefore a sheaf, the sheaf condition is the same thing to say that a functor, that's an object in this category, is orthogonal to all these morphisms. Meaning that when you apply this thing, and every morphism from here is uniquely stained to here. So this being isomorphism is exactly the sheaf condition. This holds, this property can be solved in every locally presentable category if the family is small, because we have a structured theorem on locally presentable categories like the category of the pre-sheaves, and provides this solution of the reflection problem by an orthogonal problem. Therefore, the category is reflexive. Of course, we can do the same argument considering sheaves, or not over sets, but over every locally presentable category, because we can do the same thing and note that a category that is locally presentable are the categories of the models of a sketch given by diagrams and finite limits in general, because you can interchange both the constructions. So you can, for instance, consider this adjoint for the category of internal groups, etc. So it's the main point. And this kappa is related to this cardinal because of the construction of the theorem that we can find in Adamek-Kozinski book. So it is also a monoidal semi-cartesian category with this reflection of the Day convolution. That's the formula. We extend the convolution, the tensor product on the category C, that in this case is the quantale C, to the category of pre-sheaves, and it has a parameterized adjoint, let's say. That's I call it explanation for this tensor product. This category is not a topos in general because of this result. Let me explain why this is the case. So, in general, if we have two monos, F and G, we can consider the tensor product of them and produce a certain, we have projections because the category is semi-Cartesian, and these parallel arrows in general are not the same, but we can consider the equalizer of this. So we have an induced arrow. This is not a mono in general, but since we have a locally representable category and the subobjects are in fact a complete lattice, we have extremal mono factorization, so we can factorize like this, and so this is the star construction. That's here, and we are able to explicitly calculate this for this hope factor. This gives an interval that is semi-Cartesian but not unital quantale in general. Therefore, it's easy to produce examples where this quantale is semi-Cartesian, but it's not a local, so it's not a Heyting algebra, so therefore this cannot be a topos. Even an elementary topos cannot be whole. For instance, if we take the ideals, the quantale of the ideas of a non-preferred ring, this is the case, like 0 of x. If we assume some extra properties on the quantale, like I will not define this in details, but best approximation from below, from above. There are conditions to hold this. Best approximation for below holds for every semi-Cartesian quantale, but from above it's more difficult. We have some variant notions of subobject classifier that in the case of locales they coincide. This for omega minus not so difficult, but they not classify all subobjects. Just some monos, and the classification is not one-to-one. It's more like surjective classification. But for imposing many other properties on the quantale, we have another prescription that in fact is a subobject classifier. So this imposes that the underlying quantale should be also a locale. Maybe we don't know if it's imposed that the times operation is the same thing as the IFMA, but maybe. And if I have 10 minutes, I can explain a little bit of the generalization that is the work of, ongoing work of Mariano Hugo Luiz. So this generalization is more in the sense of Grothendieck topology. We merge two words, topology and linear. That's why we put L. We're not very convinced that it's the best idea. Maybe the word montology were best, from monoidal and topology. But we are not sure that this is the best one. Why linear? Because we suspect that the internal logic that is represented by the locale, let's say, is semi-Cartesian locale. It's of some form of merging between MV algebras and Heyting algebras. That's in the complete case corresponds to semi-Cartesian quantales. In propositional case became a BCK algebra that is lattice also. And so the internal logic may be a kind of linear logic that does not satisfy contraction rule, but it's a logic with resources, but satisfies weakening. So a kind of affine logic maybe. That's why we put L. Okay. So a Grothendieck pre-topologies in a monoidal semi-cartesian category with finite limits is more or less the same thing, Grothendieck topology. We have to explain what is a pseudo-pullback is. It is the same thing as a pullback, but we replace times by all times here, by the monoidal product. Since we have the hypothesis of the semi-cartesian, we have projections, we can write this diagram. And the conditions of Grothendieck pre-topology are 1 and 2 are the same as in pre-topology, but stability is not reasonable required for all kind of morphisms. For instance, for we chose an object V, and we have a covering Fi. We have just the stability for products for the projection, like this, in both sides. And so we split the stability axiom in two. This one, and this another, that's a bit more technical. So in usual Grothendieck topology, we have the pullback of a covering covers the object. This is not the case here. You put the pullback, pseudo pullback of a covering gives a covering of this object, this other pseudo pullback. Of course, when we have the semi-cartesian quantale, this gives a, with the soup, this gives a Grothendieck pre-topology, and axiom 3, 1, 2, 3 implies 4. And when we are in Cartesian visual setting, Grothendieck pre-topology is the same thing as Grothendieck pre-topology, and axioms 1, 2, and 4 implies 3. So this means when this is product, it is just a case of a pullback. And we can mix these two strategies, produce a product of pre-topologies, and a product category is still a pre-topology. And the notion of sheaves is the same idea, but we replace the times by the pullback by pseudo pullback. In fact, a pseudo pullback is not, in general, even a weak pullback. So this arrow here is not a mono. So it cannot be characterized by sheaves. And a Grothendieck locus is just a category that the category of sheaves for this for pre-topology that is locally small, complete as explained. Because of this reflection condition, we have the scenario of Adamek-Kosinski theorem. It's an accessible category and is semi-Cartesian category, monoidal semi-Cartesian category with this product. But to get monoidal closeness, we have to get another property that we don't know if the 4 axioms already imply this, but that's equivalent to require that this relativization of a sheaf is still a sheaf. So if F is a sheaf, F of U times something is still a sheaf. This holds the category is a quantale, or if the functor all times preserves equalizer, or if holds another technical axioms that involve some factorization. And of course, there are many other possible approaches to what Grothendieck lopus should be. For instance, we can try to dig from this side, consider the Yoneda embedding, and suppose that it has a left adjoint that's monoidal and preserves pseudo-convex. I don't know if the one thing implies another in general. So for future works, we intend to continue the exploration of the properties and provide some possible categorical axiomatization, not like in Giraud sense, but in Giraud spirit idea. Of course, we have to think about much more about what should be an elementary topos, lopus in this situation. What are the right categorical axioms? And the work of José Alvim is still ongoing. It tries to produce some presentation, some idea of what should be an elementary lopus from categorical logic side, providing some generalization of the notion of the tripos in this monoidal or linear setting, and provides this tripos to topos construction in this new scenario. And of course, this is our main homework for us and my students is understand very well the work of Isaac Stubbe on rigid quantaloids, and to provide a precise relationships between these two approaches. So there is some work of Ana Luisa, Caio Mendes, José Alvim, Caio Mendes, and that's it. Thank you very much.